Okay, welcome everybody to the next semester and to the first seminar in this spring semester. I thought I would start with this topic of data science because this is something that I kind of work on recently in terms of trying to find out what it is, because it's a buzzword, and there are many books about this. Some of them not really that good from our perspective, but still it's good to see what people believe data science is. So I thought I would share this with you so that you can also do your own investigation and also hopefully broaden your perspective in terms of when you take all those courses that we have here in our program. Okay. So, so here are the slides. Again, this is just my point of view, and it seems like if you ask somebody in computer science, they would tell you something different what data science is, right? Or maybe even in statistics, they might tell you something different. So this is just my take, but I think it's kind of reasonable, and I did, looked at some courses that are being taught. Let's say there is in Coursera, there is the whole sequence of nine or 10 courses, depending how you count, in data science, and I'm familiar with that material, and also some books. So I think it is kind of reasonable view. So. In terms of a very short definition, the first bullet here, data science is the science of extracting knowledge from data. Okay? And when I look at this definition, well, essentially similar definition was used before just to describe statistics. Okay? So, as with any, this type of brief definition is obviously some simplification. But yeah, always, this was the idea that in statistics, that was, the task was to extract knowledge from data. So this didn't change, but, there are some new things that are being emphasized in data science and kind of, merging, a little bit other fields. So, statistics is obviously a big part of data science, but there are also other elements. Another issue, I think, is that, in terms of the whole process of data science, it's probably not very realistic to think that one person can do all of it. Okay, so it typically will be team effort. Well, there are some sources that claim that, yeah, those data scientists, they can actually do everything, but yeah, I'm not buying that, okay? So, yeah, one way of looking at this data science is to look at this flowchart. And as you can see, the things in terms of the data start here, with the world as a whole, where various types of data can be collected. So the first arrow here leads to raw data that is collected. And this may mean all types of sensors, images, and so on. And these days, there's more and more various types of data collected. And typically, statisticians knew that the data need to be collected, and obviously there's also, the big field of design of experiments and also surveys. But statisticians never get really into, all those technical issues, right? And also, let's say, images. Yeah, that's really, taking images. This is like, taking us totally into a different field. Right? But anyway, once the data is collected, it's there, and then it needs to be processed. And then, statisticians, know a little bit about processing data, but as long as it is relatively simple. But still, this is, I would say, mostly the domain of computer science. Okay? Also, I didn't mention this in terms of the raw data collection, but as you can imagine, whenever it becomes more sophisticated and requires more computing power and so on, so that will be to the large extent the domain of computer science, okay, but also information technology, IT. But in terms of like if it is science, then probably would be called computer science. So I would say, yeah, at the entry here, especially these days, there is a larger component of computer science. And then we go into, once this data is kind of preliminary processed, then we get into another step that we can call cleaning data. This is definitely very much a statistical part, okay? And that was always emphasized a lot. And one of the tools that probably all of you are familiar with is exploratory data analysis, which kind of, there's here one arrow, and so again, this is kind of like a simplification, but often what happens is that you actually get arrows in both directions. So you clean the data a little bit, as much as you can tell that definitely things are not looking good, and then do exploratory data analysis, and then there's arrow back because that analysis tells you that it needs to be cleaned further, right? So there's always, a feedback loop here. But once you are done with this cleaning and exploratory data analysis, then you might be able to do some models and algorithms. So this is this next box here, and this is obviously, a huge part of statistics. Actually, statistics is like mostly there. In fact, in terms of academically, because we also need to distinguish, academically, what we teach and also what is happening in the real practice, right? So, when statisticians work in, some real companies and do statistical analysis, they need to do a lot of data processing, cleaning, and so on. But we don't teach this a lot because it's kind of, from our perspective, is common sense and obvious, right? Maybe sometimes we think it's too obvious, right? But so you still need to have some skills in programming and so on. But there's not much theory about this, right? Maybe a little bit. So that's why we don't. So that's, I guess, our excuse that we don't spend too much time on this in academic courses, right? And mostly concentrate on statistical models because, well, this is difficult part, so we need to teach this a lot, right? So I will actually be spending a significant amount of time also on that, models versus algorithms issue, because I think it's pretty crucial. But anyway, once you are done with this modeling and algorithms, then you can move into drawing conclusions, which is basically here kind of written in two different ways. It can either be in terms of communicating, visualizing, and reporting, right? Which is basically, giving the message out there to somebody who can then make a decision, right, based on that information. Or it could also lead to a data product. Probably this arrow here probably should be, going maybe from this to, once you communicate and have the report, then you have data products, whatever, Again, this is just an approximation, plus, I was able to steal the chart from internet, so why not, right? But anyway, we have this data product. So what it means is, we spend very little, if any, time on that in statistics. So this is like a permanent conclusion, meaning that now you are changing the way you collect your data, right? Although, when I teach statistics, I always kind of envision this situation that, okay, we build that model, and the model has some variables, and the purpose is for the foreseeable future, use those variables to predict outcomes, right? So, potentially it could be a, data product, right? That is spitting out something. But we don't spend much time on this because it's kind of, at the theoretical level, it's pretty obvious, right? Now, details may be, more complicated, but details will depend on each case, so it's difficult to talk much about this without spending much time on, each individual case. Okay, so this is kind of like a, general overview. And then kind of, I prepared this next slide to a little bit summarize the steps from the previous chart. So at this end of raw data and collecting the data, I basically wrote this now as databases and other sources of data. Okay, so like data streaming. And then we have data processing, again data cleaning and so on, models, algorithms, and practical conclusions, data products. So in this slide, I would say traditional statistics field of statistics concentrate on the middle part. Let's see if I can. Yeah, I don't think I can highlight this now, but basically, this starting with data cleaning. Oops. Data models and practical conclusions. Yeah, practical conclusions again. I think we probably should be spending more time in courses, but again, we kind of tend to think that this part is obvious and everybody can figure out this, right? What it means. So, so ultimately, mostly it's really data modeling and algorithms. Again, academically in courses. But in the real world, actually, statisticians might spend like 70% of their time on just data cleaning and preparation. Okay, so it looks differently. Here's another view that I found online, and I think also in some books, they use this chart. Okay, this chart actually circulates a lot. So I mean, it's good and bad. Here these hacking skills. After some thinking about this, I wasn't exactly sure what that means. Because even the word, when I started, checking what really hacking means, apparently there's no disagreement what this even means exactly. Because some people, there's apparently, the community of computer science, programmers, I should say, programmers, who think very, very highly about this word, and is kind of disappointed that it started to become associated with, trying to break security of systems, right? Which is kind of like probably the most often used, as this term is most often used as, a hacker is somebody that illegally gets into a system, right? Through security. But apparently some people don't like that association. So anyway, so there is disagreement what it means exactly. But I think in this context, to the large extent, it probably means somebody who is trying to solve a problem through trial and error, right? Because this is really, this is one way to get into a system, right? Through the security, you try different things, right? So this is probably, the closest, this approach obviously has good parts and not so good parts, right? It definitely doesn't, well, science is a little bit trying and error as well, but you need to be, trial and error is okay, but you need to be educated. You need to, educated about the background, but also do this in a wise way. Let's put it this way. Shouldn't be like total random. Let's put it this way. Okay. So. Yeah, but I kind of like this this part here where it says machine learning, that is outside of substantive expertise, okay, meaning about the field specifically that is studied, and then once you add that specific knowledge of the field, then it becomes data science. So that's the part that I like, because really one of the issues that I can see is in machine learning is that people spend too much time on simply, running algorithms and not caring about what the variables are, okay? Which, is to some extent might be okay, but once it gets into the culture and it's just the way of doing things, that may not be good. And then traditional research is right here, which is also probably true. So this is basically where, statistics is. As kind of more pure statistics, right? I mean, we still like to think that statistics is part of data science as well, but kind of this traditional statistics that is being taught in still in most academic courses is probably somewhere here. Hopefully, maybe also a little bit part of data science. Okay. Also, I thought I would a little bit talk about like brief history. I mean, it's not really history, so I didn't want to even say history. It's just some events, right? One of the events is actually this. I don't know if people here are familiar with this concept of KDD, knowledge discovery in databases, because this is more a term that was pretty hot in 1990s. As kind of an extension of data mining, where data mining would be like a tool, and this knowledge discovery in databases would be basically like when you read an article about this, basically sounds exactly like data science. Okay, it's basically like that, because if you think about this, what data science is, the way I presented this, is like you have a core here, right, with the models. And then there is like the front end, right, where you need to prepare the data and kind of expand in that direction, and then this end here, where you draw conclusions and kind of expand on that, right, with the data product. So this is exactly, if you read those KDD articles, this is exactly the same thing, pretty much. At a certain level. Obviously, you will find some differences because they mostly talk about data mining, not about statistics. So maybe that's what is different. That now kind of everything comes together, which is kind of not unusual, because I'm seeing some parallels to something that is called Lean Six Sigma. I don't know if you're familiar with this, but I'm sure you heard about this. Before it was Lean for a long time, but there was also Six Sigma. And then people realize, well, why shouldn't we put the two things together and kind of also have more general process thinking? So maybe this process of data science is similar, right? People were doing, in the past it was, let's say, data mining as totally separate from statistics. And now maybe all these things hopefully will come together, and kind of everybody will realize that we need to use all the tools. So that was one interesting thing about this KDD, that it was almost the same thing. So in fact, this is probably why some people say that what is really new about big data is actually not about it. I think the context was, was it about the big data or data science? Now I don't remember. Because the two things, by the way, the two terms are often merged together. But somebody said about one of those or both that what is new about those is the new name, basically. So, so those ideas basically circulated around for some time. Also, another interesting thing is that already in 1997, well-known statistician Jeff Wool advocated that statistics be renamed data science, okay, because he thought that was a much better name. And I agree, but it was kind of going slowly, and still is unsure. It is unclear if it would be renaming or just putting under a broader umbrella. We'll see. And then there were some other voices. 2001, Cleveland also had this action plan about expanding the technical areas of the field of statistics. So what basically this means is that what I was saying earlier, right? We have this technical field of statistics, and then we want to expand into computing and and also spending more time on conclusions from the analysis. So, and he wanted to call it data science. I think he also said that, well, now is the last moment. That was 2001. Now is the last moment. Is still the name. You can still take the name, but I guess statisticians were late to this, and to the large extent that this term is now taken over by computer scientists. So, okay, and then another event is this article by Leo Breiman about statistical modeling, and basically two cultures, and I have another slide on this, and this is mostly about the relationship between statistical modeling, traditional statistical modeling, and algorithms. Okay. So let me talk about this more later. Going back to Jeff Wu article, so he basically mentioned what he calls statistical trilogy that consists of data collection, data modeling and analysis, and problem understanding, solving, and decision making. So again, if you look at this, well, it is simply, some part of this picture here. Right? So again, the same idea is repeated again, except that now more attention is being paid to this, initial process because there's more data, so there's more need for processing and also a larger variety of data and so on. So more time is spent on that. And let's talk about big data, okay? Because this is often associated with the concept of data science. So the first question, is it new? Okay, so so let's go back to 16th and 17th century, right? Did people have large data at the time? Well, everything is relative, right, to your computing capabilities, right? So what I'm saying here is, and this is true, that Kepler, we are talking about early 1600s, and then Newton and Kelvin, they all complained about spending way too much time on calculations. Because so the data that they had, because they had some observations, some astronomical and other things, the amount of data that they had was too large for their computing capabilities and the technology. Right? So people were always thinking about, and also, so this is one issue, the data. Second, tools, right? Because people think about, okay, now we need to have new tools because it's so large. Well, yeah, this was always the case. All the time you need to have new tools, and in fact, it's totally not incidental that people came up with the idea of logarithms, which was exactly 1614 year, exactly because they needed to do some calculations, and you could speed up multiplication significantly with logarithms. That was the main, because now you may be thinking about logarithms mostly in the context of the logarithmic function or logarithmic scale. But actually, the main application was actually multiplication of large numbers. I don't know if you are aware of this, because maybe you might be too young. But I know that I saw in my parents' library, I remember seeing the table of logarithmic numbers. So you would just and it was actually used a lot because people would just find the logarithms and then add them and then go back to the original number. So that was the reason. And then actually, if you think about this, definite integral is also very important for computing power, even though you and myself also, I first, when somebody talks about definite integral, I'm thinking about a function, right, and calculus. Why is it called calculus, by the way? Well, maybe because it's, it was actually used a lot for, not just calculating the, integrals and differentiation, but for calculating actual, in the sense of computing. Because if you think about this, as you remember, definite integral is like a sum, right? Theoretically speaking, we're talking about convergence, but for a long time, before 17th century, people were calculating a lot of things by piecing together things, like, for example, area, right? You can almost any object, you can just divide into small pieces and do calculations, but that's a lot of work, right? So integral is a great help, okay? Simplifying calculations. So we need also tools for the 21st century, right? So this is not surprising. So what are some characteristics that people talk about in the context of big data? The people talk about these 4 V's, okay? So those should be words. Those should be the words that start with V, right? So they came up with these: volume, which is simply, you know, the number of observations and variables. Then the variety. And this is actually huge because, you know, before, statisticians were typically just, you know, picking, because you often can pick the problem that you can solve, right? You are not trying to solve everything, right? You're trying to solve the problems that you can actually solve. So they were just working with, you know, numbers, right? Because that was easier. Now it is also possible to work with unstructured data, including text, including images, videos, audio, you know, anything. Right? So now it is possible, so now that's why people do it. Right? So this is probably the most challenging aspect, because actual, you know, theory is, you know, probably, you know, significantly behind. I mean, obviously there are methods, but yeah, it is difficult. Then also velocity, which, you know, is relates kind of to volume as well, but this is like volume per minute, right? So, so depending, you know, what needs to be handled. And then also the fourth is sometimes mentioned as the value. And this is also, I think, something that is relatively new. I mean, people always knew that it's kind of good to analyze data, but now it becomes also the business value, right? We hear about Amazon and other companies that make money by analyzing data. So that's business value. But also, I think another meaning of this part value might be the scientific value. Although here, I kind of, you know, wasn't sure if I should put a question mark here, because, you know, on one side there's scientific value because you can draw a lot of new conclusions from, you know, a lot of data. But then also scientific value sometimes is with a question mark, because a lot of those large or big data are mostly what we would call observational studies, right? It's not an experiment. So that obviously means that conclusions can be shaky here, right? I don't know, hopefully you had this somewhere in your courses that, you know, if the data is not controlled, if you have only observational studies, then it's very difficult to draw conclusions from, let's say, correlation to causation and, you know, those type of issues. So, yeah, so I think because it is observational data, then we need to be very careful with drawing conclusions from any analysis. More about data science. I think, you know, I think the focus should be on science here, because there's also, like, you know, these two words, data and science, and some people put more emphasis on data. I think we should, you know, put more focus on science. And then there's also too much hype on data size and the tools, okay? Especially data size. You know, in some circles, if, you know, if you are below 1 terabyte, yeah, that doesn't count. You are not data scientists, for example. So I think this is very questionable, because I definitely appreciate the complication from the size of the data, but the point is that even if you have terabytes of data, the question is how much of the data is really relevant, for example, to a given question that you want to ask. That's one thing. Second, it's likely that all the data is from what we would call in statistics from different populations, right? Which means that, you know, let's say you collect the data, you know, today, and then, you know, 1 month later. Or let's say you collect this every day, like streaming data, right, all the time. Well, this is, you know, a different, depending how you treat this. Either you can treat this as a separate population. You can find some, you know, cycles, right? So depending, you know, what you do exactly, but you know, typically there are many ways to, you know, simplify this and actually think in terms of smaller numbers, not necessarily, you know, all those terabytes of data are not always all that valuable. Okay, so there might be sometimes, but you just need to be careful about this. And I start thinking that, you know, one reason that people don't concentrate that much on the science part is that, well, it is more difficult, right? I mean, it's kind of easy to point that, oh yeah, I got this huge data and I know how to process this, how to write a program that would do something with this. But does it really have scientific value? Well, that's difficult. In fact, I was working, for this presentation and also for some of my future presentations, I was working on several examples. And one of the examples got actually pretty complicated, more complicated than I thought. So I scrapped this from today's presentation because there were some, scientific questions that I was not totally ready to address. Hopefully we'll be ready next time. So yeah, so things actually come up unexpectedly. And they actually come up when you dig deeper. Because if you just take the data set and you just say, well, okay, this is just here, these are my inputs, these are my outputs, and I'm not going to worry what it all means, what the meaning is, then you don't have issues. Really. But once you start thinking about those, then it becomes more difficult. In the second last bullet is basically about emphasizing, because sometimes when people discuss data science, they kind of get carried away and they think about the fact that science would relate to addressing sciences, but not problems in engineering or simple things like popularity of movies, right, and so on. So that's why I'm emphasizing here that the science, that the problems are in various areas. It could be anything. The science part is that there's this scientific approach to data. Okay, so if you discover a tendency, chances are, or a pattern, okay, chances are that pattern will hold in the future, right? That's why we talk about statistical significance, right? So that it holds in the future and has some real meaning. So yeah, so that's why I'm also saying in the last bullet that that impact will be measured by the questions that you can answer scientifically with the data. So it's something that has a longer-lasting impact. Okay, so in the next slide, I want to move a little bit into this topic of data modeling versus algorithms. Okay? Because I think this is a very important topic, both in one of the key issues I think still being discussed in data science, but also in your academic courses, because when you take some courses like regression methods and some of the more traditional approaches, even also in multivariate analysis, right? But also we have data mining, right? Course, and so how do we put the two things together? How can we really believe in algorithms without any model? Right? So these are still kind of to some extent open questions and still being discussed. So this slide is actually mostly based on that paper by Breiman, but this is kind of ideas that express kind of general thinking in statistical world. So let's start with thinking about a process, a black box process. So we don't know anything about what is happening inside, and we have some inputs x and some output variables y. Okay? So, and let's say we collect data on those, right? So we have some data about x and some data about y. So then in general terms, there are two goals in analyzing data. You can either do prediction, so you are just trying to, in the future, you are trying to predict outputs, the responses from the future inputs, right? So it doesn't matter how it is done as long as it works. Second approach is basically about concluding information. So it's like, mostly talking about interpretations, but, I phrase this in general terms in terms of information. So somehow understand how the process works. But what I mean by this is that, not really, the exact mechanics, but just in the sense that, well, for example, if I take a linear combination of x variables, this is my predictor of y, right? This is a linear regression model, right? So now I know that, well, each time I increase x1, let's say, by 10 units, and then let's say coefficient is 2, right? So that means that y increases by 20 units, right? So this is what I mean by, explaining how the process works. Okay? Not in the sense of, not in the physical sense, but in the statistical sense that I can pinpoint those statistical properties. Okay? Or at least give an equation, right? Because later on I'm actually going to talk more about specific examples. The question is, in some methods may not be that easily interpretable like linear model. Let's think about, the second degree polynomial, a quadratic function, right? A little bit more difficult to interpret, right? Because of this square term, this is not a linear, it's not like a proportional increase. On the other hand, it's an equation, relatively simple equation. So it's still pretty good interpretation, right? And then the equation may become more and more complex. So then interpretation is more difficult. And then finally, you have those algorithms where there's no equation. Okay? So it's even more difficult to interpret. Pretty scary, right? No equation. How come, right? In mathematics, it's not supposed to happen. Right? That's why this whole thing of machine learning is kind of still not that deeply embedded in mathematics and traditional statistics. Okay, so what so more specifically, Breiman is talking about these two, what he calls cultures. Okay, so the first one is data modeling culture, and it assumes a stochastic model of the form where the response y is a certain function of predictors x, noise, and parameters. Okay? So if you have linear combination, you have these parameters, and at the end you say plus epsilon. Okay? That's a simple example. But it could be any combination as long as it's specified. Okay? So this function is specified. And then at the time, he estimated that 98% of all statisticians are members of that culture. Okay? That they prefer this approach. And then there's this other algorithmic culture, which assumes that the process is complex and unknown, and it tries to find an algorithm to predict y. Okay? So in essence, there is no model, but it's just some ways of calculating simply the answer y. Because and by the way, as you know, but maybe I should mention this, that in the previous approach, when you have that stochastic model, in order to do prediction, first you assume that whatever model you assumed is, at least approximately correct. Doesn't have to be perfect, but at least approximately correct. And then you estimate, let's say, parameters. Right? So this is the part that comes from the data. You estimate parameters. So it's like an intermediate step. In algorithmic culture, there's no intermediate step. You just have your algorithm. And Breiman estimated that culture as 2% of statisticians and many other people in other fields. And I think that's pretty accurate, probably. Now these days,
still true today, or
no? What I'm saying is, at the time it was true, probably. These days, I think the numbers are different. I have no idea, obviously, what they are, but still, I would say there's significant percent is in the data modeling culture. Maybe 80% or more. Well, also, maybe these days there's more and more people that kind of believe that we should use both, right? This previous concept that I mentioned, that now like with Lean Six Sigma, same thing with this. People start believing that, maybe after all, maybe guys, we can use algorithms, right? But still, I would say 80% in the sense that most statisticians would prefer and would put more emphasis on trying to find a model. And actually, myself, I definitely would prefer to, if I can, I would definitely give more trust to a model. And I think, this is actually a good approach to always try to find that model if possible. In fact, I'm thinking that one way to approach might be that build that if you really have a complicated case, run that algorithm, and if this is all you have time for, maybe that's it. But if you can spend more time on the problem, then you should probably treat this as exploratory tool that basically tells you how this process works, and then try to find a model that would do almost as good. That's one possibility.
Maybe you could have a seminar with a representative of each culture put on a debate for us.
Yeah, that's a good idea. This might be pretty hot. Are you ready for that?
Yeah, I would.
Can't be any worse than the holy war between the Bayesians and frequentists.
Yeah. Don't even throw in frequentists here because that will only complicate issues. Okay, so that would be interesting. Some other items here that I want to mention. In terms of those points of contention, in the sense of the still ongoing debate, when I was thinking about this, two things I think seems like the most important. The first one is computing versus modeling and prediction. So, obviously, if you go to computer scientists who do data science, obviously they will tell you, of course, prediction is important, but still they would spend a lot of time on simply computing issues. Okay? So that basically leads to a question: how large the slice of computing the slice of computing should be in data science. So I guess I wrote this as how large slice of data science is the computing part. Okay. So, and again, different people will have different answers, right? So if we bring those people into one room, right, at certain risks, right, they will, tell you different things. So we obviously, from our perspective, we believe that that computing, as important as it is a little bit, kind of a different field, and it has some part, but modeling and prediction is more important from our perspective. And also, in terms of the second item, in terms of how large data set needs to be, here I'm actually in favor of not having any limits. So, data science is just data science. Okay, if you have one number, well, that's not good, but it's still data science. Okay. Maybe you should have more than one. But it doesn't matter, Or you can basically say, well, if I have one number, I can't really do science, but, well, that's my statement, that because of what I know, one number is not good enough. You should still be including those small data sets into the picture. And then the second point of contention is the issue that I mentioned earlier, modeling versus the algorithmic prediction. So the same questions I already mentioned. Is it acceptable to predict using a black box algorithm? Or do we need to understand the process better for reliable prediction? So certainly I do believe that if you run a black box algorithm on observational data and then hope that this will work in the future, well, this is pretty, potential might be very questionable, I would say, right? Because you don't have a physical mechanism that would explain why this is happening. So you're really on a shaky ground, And obviously those algorithmic people, they will lead you to believe that cross-validation is the solution, but well, no. I mean, cross-validation is only as good as the original data that was collected, right? So it's really the best way to get outside of the data. There are two ways. Okay, one is collect more data, which a lot of students. If I ask the question, or a question, if I ask a question, often students say, "Oh, we need to collect more data," but that's not a good. This is not a good answer because, well, yeah, obviously you can always collect more data, right? But at a given moment, we always want to assume that that's what you have is that's all you have. So the best way to get out, to extend this outside of the data is that physical mechanism, right? That also leads to conclusion from correlation to causation. So another slide here, talking about. You remember I mentioned the interpretability of traditional models and difficulty with interpretation with some other models. So this is another view at this with basically two variables, interpretability and flexibility. Because when you build that second-degree polynomial, why do you do this? Because it's more flexible, right? Make easier adjust. And then if you go further with splines, let's say, I don't know if all of you heard about splines. This is basically like fitting, let's say, sometimes on just first-degree, polynomials, so straight lines or second-degree or third-degree, into small pieces of data, piecewise, basically. So you lose some interpretability, or maybe a lot of interpretability, but you gain flexibility. So on this scale, this is pretty much typically what happens. That we will move on this diagonal. So typically, if you increase flexibility, you typically lose interpretability, and vice versa. So these are here, very much, machine learning methods here. That is difficult to interpret. So this is why I'm actually advocating to use those methods if they really improve prediction, and then see if you can, to the large extent, if you can actually get similar results with simpler, more interpretable methods. Okay? And in fact, I have one example where I was able to do this because, in fact, this is actually the data set that didn't make it to this presentation. Also, time-wise, and there were more and more scientific questions. But one of the examples in the Breiman's paper is an example about the liver data, and he actually shows that he gets good results with random forest. And what I was able to do was to use Box-Cox transformation on the variables, and then use the regular linear discriminant analysis and get almost the same results, if not better. So, okay. So now I want to show you some numerical examples. A lot of slides, but we should probably get through this pretty quickly. So this is what this is actually artificially generated data, and also there's only one input X and one output Y. Even though most of these methods that I'm going to show you, the main idea is, and the main application area is when there are many variables. That's when they work best. But the problem is that if I have more variables, I cannot show you a plot, right? So in that 10 or 100 dimensional space, it's very difficult to show what's happening. Right? So this is purely for educational purposes, just simplifying to X. So let's say this is this small data set with n equal to 20. And here, you know, this straight line almost fits, right? Well, maybe not quite, right? Because it's a little bit, you know, these residuals are a little bit too low, maybe, right? But I would say, you know, it wouldn't be that terrible approximation if we just use a linear model, or you know, a first-degree polynomial. So let's now think about the second-degree polynomial. And this is way better. And even though, you know, some of the points are actually below the line, I think there are too few to actually be alarmed, right? So also, if you look at the plot of residuals, what do you think? I mean, would anybody here object to this model? Looks like almost perfect, right? Okay, so we are good here. Okay, now when I increase the sample size, and this is from the same process, which means, you know, in my case, from the same model that I did the simulation. When I increase this to 50, now I start seeing that, well, this tendency is actually more pronounced, right? Also here, see, a lot above and then below, or even here things are happening. And if you look at the residuals, you see this even better. Because now I'm really getting suspicious, right? It's starting high, and then it's going low and high again and low, right? So maybe I need to do something with this. So one of the tools is actually this, what I mentioned earlier, regression spline. So the idea is actually to put together pieces of polynomials. And in this case, actually, all of these pieces are linear, okay? Because, you know, this method, if it doesn't see a major improvement, it will not go into, you know, some more smooth lines, right? Which, you know, first when I looked at this, I was a little bit disappointed, and I was actually trying to force the algorithm to go into more, you know, curvy lines, but it didn't want to. So, okay, so then I was thinking, well, maybe that's not actually that bad because, well, we know that the simpler the better, right? And actually, the more you think about this is this interpretable? Okay, and which, you know, one way to check this is, would you be able to explain this to a non-statistician, you know, these results? And the answer is, yeah, actually, exactly because these are linear pieces, I can very nicely explain, because I can say, okay, in the first part it's just constant, right? And then increases at the constant rate in a certain interval, and then next interval it increases by another fraction, you know, another at a different rate, but a constant rate, and so on. So, yeah, very nice. Okay, so that's one possibility. Another popular tool is what is called regression tree. Which basically means that you have like a decision tree that for certain ranges of values. So let's say it might basically say that, okay, if x is less than 5.5, which is I think somewhere here, do this, and if x is larger than 5.5, do something else. Right? And in this case, actually, it decided that if it is x is less than 5.5, just constant value, okay? And then if it is larger than 5.5, then, well, I need to split this again. That's why it's called a tree, because I need to split it again and basically say, okay, if x is, let's say, larger than, it's almost 7, it's probably like 6.8. Sorry, if it is less than 6.8, right? Then it is constant. Now we need that group, right, on the right. But if it is larger, do something else. And then you dig deeper, and you can build like the whole tree, right, of decisions, what needs to be done. And then finally, at the end, you need to specify, you know, what the value is. And you just say, okay, a fixed number, that's why it is constant on pieces. Okay? Piecewise constant number, constant function. So, I mean, technically speaking, you know, I shouldn't have these vertical lines, but, you know, it would take more time to get rid of them.
So is this
Did you think of this as being loosely equivalent to splines, but you're forcing a very particular piecewise function for splines?
Well, yeah, it's a very similar idea. Obviously, the splines for continuous functions, they will typically work better, right? And here, I'm glad you asked this because, and then you are definitely right. There is, there's significant similarity because we do piecewise. On the other hand, in splines, we try to keep things continuous, right? Because we have continuous variables, right? And for this type of data, this will typically be, or if not always, will be a better approach. The tree, this regression tree for this type of simple data with one continuous variable is just not the right tool. I'm showing you this only so that you see how it works, right? Now, if you have a more complicated situation with, data, in many dimensions, and also, let's say you have categorical variables, right? The tree is very handy, right? Because now you say, okay, if your values of your variables are A, B, C, you cannot do spline, right? Unless you divide, different splines for each case, but the tree would just ask you, is it A, okay, or is it B, or is it C, right? And then you can build the tree. So it's just a more flexible tool. Yeah, tree is more flexible. And then there are those even more sophisticated models. Like, for example, one of them is called stochastic gradient boosting. And we're not going to go into details here, but the point I wanted to demonstrate is that now the relationship is very shaky, right? So you might be concerned that, well, why is it suddenly going up here, right? Probably because of this point here, right? And then it's going down. So especially, there's some, let's say you are trying to model this for a scientist, and let's say we know that in certain, this whole function is not actually monotonic, but let's say if there was a monotonic that when x goes up, y is supposed to go up, right? And then suddenly you get something different. So that's not good, right? That's one reason. So in general, it's more difficult to justify, this jittering here, and also more difficult for interpretation. Well, in fact, talking about interpretation, there is no formula. There's no formula for this, right? It's just an algorithm. So, okay, so that's for n equal 50, and then I'm running this again for even larger data set, 200. And now you might actually start even guessing what my function might have been. At least you know that it was pretty wiggly here. Actually, what I did, I just took a second-degree polynomial and then added a sine function to that. Okay, so that's why I got this, and I needed to do a little bit of experimentation with the coefficients, right, so that it looks right. But that was the function. So now let's see how those methods work. From the second degree, you really get huge problem with the residuals, right? So it doesn't look good. The regression spline still doesn't want to move to anything smoother than straight lines. That surprised me a little bit.
That's still not
But it actually works, right? It actually explains pretty well. So that makes sense. I mean, it surprised me in the sense that I was hoping it would, move to smooth. But when I look at this, yeah, it's a pretty good fit, right? And the regression tree actually looks very similar. It actually only added one extra step. Still, not bad. Right? And this is the stochastic gradient. So it actually added a little bit more jitters right at the beginning. But it's actually, it's definitely a very good prediction. Okay. So if there are any questions?
So I guess my obvious question is if you want to preserve interpretability, and say I mean, I've never used the stochastic gradient, so I have no idea. But like, let's say that was all you had to go with at first. Are you then? Is there anything in particular that you're using to kind of evaluate performance of these other potential models?
Oh, you mean like
So if you want to go
algorithms?
from your algorithm to
Are we talking about evaluating algorithms or models?
Well, I'm saying if you want to go from an algorithm
From algorithm,
to describe
okay.
that
Right.
to a model,
Right.
do you have particular
how
markers
would
that
we
you use
evaluate?
to evaluate
Okay.
what to choose?
Well, very simple. How to find this or how to evaluate? Once you have some ideas what to use,
Yeah.
well, evaluation would be simple. It would be simply on the prediction ability, right? If it is predicting about the same, that's good, right? And if it is no, then it's not good, right? So that's the easy part. Now, in terms of knowing how to find that model, well, that's more difficult, right? Well, obviously, if it was just one variable, I could just plot and look at it, right, and get some ideas about what the function should look, right? Obviously, you can do this even without those methods, just by looking at them at the scatter plot, right? So so that's a more difficult part. Maybe sometimes it could be just by luck, in the sense that actually exactly that happened in that example that I mentioned earlier with the Bryman example, that actually I had no idea how good the box cogs with the linear discriminant would work versus the random forest. But I knew that originally, first of all, when I ran first linear discriminant function, the classification wasn't too good, and I also knew by looking at the data that they were not normal. So the obvious fix is fixed normality, right? Because the linear discriminant is supposed to work well when it is normal, right? So that's what I did, and it worked almost, if not better, actually. With some cross-validation, actually worked even better than random forest. So it was, in the sense, incidental, in the sense that I fixed the problem and it just happened to be as good as the other, right? In another case, when I fix the problem, it may not be as good, right? So. Any other questions? Okay, so thank you for coming. So yeah, we will have, you have the schedule. So for next time, here I can see, who came here. But for next time, I will prepare attendance sheet, and hopefully we'll have some interesting presentations in this semester as well. Thank you.
Another question. So for some of these more algorithm-oriented approaches, are there any particular classes that we offer that hit on these?
Second, your question is about.
So like some of these algorithm-based techniques.
Right.
Do we have any classes?
Yeah.
Cover these?
Well, we have the data mining class, right? And at this point, I think this is it. So we are still in the, in the old school. Well, the truth is that, those algorithms, there's actually a reason, why this is more often computer people, do that, because it is computationally intensive, but there's not much theory about that, right, about those other methods. And if there is any theory, it is very complex theory, and also, very, not very conclusive. So that's, I guess, one reason, why we might not be spending that as much time as we should on that. But yeah, we definitely should have more courses. In fact, I was thinking already like a year ago about starting a course on predictive analytics that would kind of address this. But but there's actually right now there are some complications in terms of our program and other things. So So it's still on hold, that idea. So yeah, that's a good question. We should have more classes. Okay, thanks again.